What are we starting with this week?
We review.
We review. How did he beat me with the delay?
Because he,
I started that halfway through his sentence.
honestly, I feel like he just tries to preempt when I start talking. There we go. So this re-review, it says, "I like your funny words, science man." That's it. Let's go on. Let's move on. That's it. Let's start the show.
Start the show.
But before we start the show,
Oh,
we've got an announcement to make, don't we? We've already made it,
Again.
but let's make it again.
okay. Dun, 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 dun. Get your SCI GUYS 2021/27 AL calendars immediately.
Immediately.
right now.
In fact, you've only got a week from the day that this episode comes up to get them at the special pre-order price of what, Luke?
$11.99, including free shipping if you live in the UK.
If you live in the UK.
Woo.
Wow, there's a bit of an echo in here. Wow.
They'll be hand packaged by my supple little hands.
And hand designed
And
by
that's priceless.
hand designed by Luke's supple little hands also. But there are plenty of cool things in it. There's pictures of us, isn't there? Well, there's kind of
Yeah.
pictures of
Well,
us.
there are a few pictures of us, actually.
A little bit. There's picture of
12
us.
in total.
Yeah.
Yeah.
12? 1, 2, 3.
13.
No, more than that.
Oh.
More than 13. Look, I'm not going to count them because there's lots of pictures of us. But there's pictures of us spliced with scientists. There's fun facts. There's little Easter eggs in there as well to a few different things. So definitely get your hands on one as soon as you can because they are limited edition. And once they're gone, they are gone.
Yeah,
We don't have many left.
There's only so many of them.
Yeah, I mean, we've sold, I think, at least half of them. At least half
Yeah.
at this
Oh.
point. Yeah.
You better get in quick then.
Yeah. So let's start the show.
Let's start the show.
Woo! Hello and welcome to the SCI GUYS, the show where we talk about the crazy, weird, and wonderful stories from the science world. I'm Corey, and as always, I'm joined by my co-host, Jamp, and Luke Cutforth.
That's me. Hi.
Well, hello there.
Today, we're talking about the optimal autism and microchip delivery system.
Oh, vaccines.
What?
Yes, bang on, vaccines.
Oh no, that was so uncomfortable.
This is not something that I believe.
Now, to be clear, there are no good data to support the idea that vaccines cause autism. Even if there were, autism is not a bad thing, and it shouldn't be a reason to avoid life-saving vaccinations.
And that's the show. You can find all the references to this episode in the description. Subscribe for new episodes every
Follow me at Jumpkin everywhere.
Today's an episode about vaccine production, and if you're worried about the efficacy or safety of vaccines, we have an entire episode to that linked in the description, and we won't be entertaining that idea today. Good?
Yeah.
Good.
Okay, right, let's get started. Actually, this, like I said, today's episode is about vaccine production. We also did another episode about the very first vaccine, so if you want to see that, that's also in the description. Anyway, let's actually start the show. So, question 1, which you guys should both know, because you've had them, and we've done episodes on them before.
Ooh.
What are vaccines?
Things you get done in your arm, some usually. And
Tattoos, maybe?
but do tattoos prevent diseases and other illnesses?
If you put a vaccine in them, yeah.
Well, there we go. We should start doing that.
We
More
should
effective.
oh my god. We saved the world. Just put tattoos. Vaccines and tattoos.
No, it's a government ploy to put the vaccines into you without you knowing.
Actually, can we just okay, before we start on the sort of
Your tattoo artist is a government agent.
Right, so I said we would God, I said we wouldn't entertain the idea that vaccines cause autism, but I do just briefly want to touch on because this wasn't really a big conspiracy back when we first did the last vaccine episode.
There was like a few people talking about it. It was like you could ignore them.
Microchips in vaccines. Here's the thing,
Yeah.
right? If the government wanted to track you, which they probably do, they already have a very good way of doing that, which is the device that you may be watching.
I literally had this conversation
on.
the other day. I was talking to someone who was like, I'm not going to get the vaccine if it comes out because I'm scared that it might be microchipped. And I was like, if they want to track you, you've got an iPhone in your pocket that knows where you are all the time and knows more things about you than you know about you.
It's a pretty big. It's not that small of a microchip either.
It is a pretty hefty
big
microchip.
and also removable.
And
But the
also
fact
costs
is,
you like £1,000.
Exactly, they make you pay for it. So the fact is that this knows what my face looks like. The other
Yeah.
ones knew what my fingerprints look like.
Yeah.
So it knows both. It knows where I am at all times. It knows what I'm shopping for. It knows who I'm friends with. It knows everything
what you're
about
watching,
me.
what you're interested in, who you're talking
Everything
to,
about me.
everything.
Everything about me is in this little brick. Okay, for anyone listening, it's
I'm-
my
Oh,
iPhone.
but the nitty bitty microchip in my arm.
I
might
mean,
break me.
I would like to point out that what you're discussing there is somewhat a conspiracy theory in that your Amazon knows who you're shopping with. Maybe your card knows what you're shopping for. Your phone, the device knows your face, but Apple claims that it doesn't transmit the picture of your face or the fingerprints to the cloud in any way. Like, there's no agency that has all this data.
But my point is, the next thing I was about to say was actually the fact that all of that information is on this, basically, right? You can get all of it from this. This uses all of that information.
If these people are so concerned about being tracked, they should also throw away their phones.
Well, the thing is that, like, okay, the easiest way for the government, right, to track the population or get them to do whatever is not to force it into them using microchips via vaccines, which people already have issues with. The easiest way to do it is to make it convenient, like the iPhone, or just, I don't know, make Apple give it to them. Just do that, which Apple probably wouldn't, because they've had a pretty good history with that.
That does sound more likely to me.
It does seem more likely, doesn't it?
Yeah.
So don't be worried about microchips and vaccines, because it's an overly complex plan, and it just wouldn't work.
They probably thought about it and gone, no, too much hassle.
No, people are already too wise to it. They'll do something else.
Yeah.
Like, I don't know.
Something people are not wise to, like tracking your phone.
Or putting a listening device in your house that also plays music sometimes. That's that on vaccinations and microchips. You can probably rest easy. And if I'm wrong, I'll put my hands up and say the government is dumber than I expected. And to be honest, I expect them to be pretty stupid. So, wow.
Maybe they are right.
Exceeding expectations. So, vaccines. Vaccines are a type of preventative medical treatment. They train your immune system to fight a disease before you catch it, basically. It means that when you get the disease, come into contact with it, you won't get ill. So, it's quite good. It's better than most other treatments that we've got, which are you get ill and we try and make you less ill. Please stop being so ill. Stop it. Oh no, they died. Whoops. Vaccines are pretty good because it's like, hey, you ain't never going to get ill, buddy.
They stop you from getting it in the first place.
Yeah, exactly. It's very good.
Very helpful.
So, this is from the NHS. Vaccination is the most important thing we can do to protect ourselves and our children against ill health, and they prevent up to 3 million deaths worldwide every year. Like I said, from the NHS direct. That's literally a quote from their website. And also they said that when from the point that vaccinations were introduced into the UK, diseases like smallpox, polio, and tetanus that used to kill or disable millions of people are either gone or incredibly rare, which is incredible. And other diseases like measles and diphtheria have been reduced by up to 99.9% since the vaccines were introduced. So there is there's no contention over the fact, there's contention over it, but there is no doubt in the fact that vaccines are effective.
Long story short, vaccines are very good.
Obviously, there are some drawbacks to vaccines. For most of the new sort of virus vaccines, the big issue is the fact that you can't necessarily make one very rapidly or scale it up very quickly. That's not really an issue for vaccines in and of themselves, obviously, but it's this sort of particular kind of vaccine. It's difficult to make it quickly, as we've seen. Given that that's what's happening in our lives right now.
It's very interesting, this, actually, because I, having not done biology beyond GCSE, in which they just sort of teach you that, or at least when I was doing it, they teach you that vaccine is a dead version of the thing you don't want, or an inoperable version of the thing you don't want, basically dead or disabled, and then you inject it into your body, and that's it, you're good. And only during COVID times did I learn that actually vaccine development is significantly more complicated than that. So thanks, GCSE biology.
Yeah. Well,
I would never have guessed it was complicated.
The thing is, it's not... Okay, in the same sense that a lot of stuff you learn in biology, this is the fact of biology, right? When you're learning it in school, all the way throughout your life, that you start off with a simple concept that is it broken down to the absolute basic of it. And then the next year, you take a step up and it's a little more complexity and you keep on seeing it in higher and higher resolution. So they're not necessarily wrong when they say that vaccines are basically just dead or attenuated is the word that we use, weakened things that we just inject into ourselves. There are vaccines that are basically just that. But vaccine development is a lot harder than just get a bunch of stuff, kill it, chuck it in. There are other steps. We got to do some other stuff. So the normal sort of approaches for making vaccines aren't necessarily applicable to things like cancer, which aren't infectious diseases. So vaccines are really good for infectious diseases like, let's say, diphtheria or measles or mumps or the big one that's happening right now. You know the one. I don't even need to say the name. They're good for things like that. The great thing is that this will obviously this won't even age poorly. Everyone will remember this. So yeah, the thing is that vaccines don't really work against the normal vaccines don't work against non-infectious diseases like cancer, I guess. So that's one drawback. You can only use it for a particular kind of thing, and also it's kind of difficult to produce quickly and scale up. And that's kind of a broad outline of what vaccines are. So why don't we go on to how they work? Because you gave a pretty good idea of how they work there, Luke.
Dead thing, put it in my body.
That's
understand.
That's called eating meat, bro.
Yeah.
Some social commentary over here. So initially in my notes, I wrote, I'll go over this quickly because we've got a lot to get to today, and we've covered it a little bit before. I realized that we haven't covered this very in depth before. And also, I now have about a page of notes on this. So,
oh, lovely! Give me that high-res biology, please.
So, yeah, we're going into how they work. Yeah. So, essentially, vaccines. We need to understand first the immune system. But before we get into that, I just want to say that I think vaccines are really beautiful. I think they're very interesting. No, honestly, they're
you're beautiful too.
Thank you very much. They're really incredible because they're kind of the equivalent in my mind, the scientific and medical equivalent of someone in martial arts using someone else's body weight against them. Building sort of, do you know when you see those sort of cities that are built into mountainsides or trees, or, you know, working with sort of nature or the landscape to make what you want? It's literally what we do is we take our body's defenses and just use that.
Yeah.
We're not doing anything. It's more natural, you could say, than conventional treatments, because you're literally just using your immune system. You're just taking a little boost.
In the same way as the Cas9 system. What was that called again?
The CRISPR, Cas9.
CRISPR, yeah, that's a part of bacteria, isn't it? The only thing is about that, though, is that you're saying that a vaccine is just using what the body already does in order to create an outcome that you want. But that's also what the virus is doing in the first place, is it's using what the body would already do, which is replicate cells, to make such a horrible destruction. So it's like we're fighting the thing in a beautiful way, but then the thing we're fighting was also doing the thing we're doing and are calling beautiful. Whoa.
I just love the idea of using really using sort of biology to our advantage. Like, I feel like, you know, like using chemistry, that's just brute force. That's nah. Use biology against it.
It's like the difference between winning a war by using brute force and like gigantic bombs, and winning a war by sowing a little discord amongst the leadership of the person you're fighting, so that they just end up fighting each other. I think much smarter
like
way of winning a war than just
Civil War.
Exactly, like Captain America Civil War. So vaccines, they use your immune system. They basically train your immune system up to fight diseases. And so before we understand how vaccines work, we kind of need to understand how the immune system works. So there are two sort of main parts to your immune system we're going to be talking about. The innate immune system, which is what you're born with, and then the adaptive immune system, which you kind of build up over your life.
Right.
And it develops whenever your body is exposed to sort of
something new.
Yeah. Well, so whenever it's exposed to like sort of microbes or chemicals or things like that. So the innate one, that is your sort of rapid response system. That's when it finds something that it doesn't recognize. Your body finds something it doesn't recognize inside of it, by the way. This isn't like you seeing a chair for the first time and breaking it. This is... crap! Oh, it's a chair.
Immune system
I see.
response.
Oh, you should have told me.
Goodness me. Well, at least I'm safe from this chair. No, so basically what happens is something comes into your body and you're like, your cells are like, I don't know what this is. You've got very special cells that, you know, kind of look at stuff and they're like,
little detective cells, like
kind of. And
have a look
they're
over
like,
there.
I don't know what this is. I'm going to eat it. So these cells are called phagocytes. They basically swallow an invading pathogen or just anything coming into your body
I don't know
that it doesn't like. It swallows it and then it breaks it down using very special enzymes. So that's the innate immune system. That's what that does. It's very simple. It's a case of...
So you're born with those little boys?
Yeah. You're born with everything. You're born with all the parts. So, but this just does this. This just does this kind of regardless. This is kind of more of a sort of okay, let's just eat it sort of situation. You know, it's not very adaptive. It doesn't do anything. It doesn't do anything specific to fight specific things. It's just like, there's a problem, I'm gonna swallow it. Okay.
Right.
So if we just had that, we wouldn't be quite as survivable as we are.
No, we'd probably die really young, wouldn't we?
We would, yeah. So there's the acquired immune system as well. What it basically does is sort of specifically target things coming into your body. So it kind of can remember things and attack them specifically. So it does that by producing antibodies. So if something comes into your body doesn't recognize what it is, or it sort of recognizes it as dangerous, it can trigger an immune response, which is, you know, the production of sort of antibodies and all that sort of stuff. You know what an immune response is? It's what happens basically whenever you're ill. All of the things that happen when you're ill, like, you know, like a fever or like a runny nose, it's an immune response. If you've got different varying levels of like sort of allergic reactions, those are all immune responses, because we'll get to it in a second as to why. So basically, your body comes across something it doesn't recognize, and it can trigger it could trigger an immune response. So something that, you know, can potentially trigger an immune response is called an antigen. And an antigen that does, or like sort of actively triggers an immune response, that's called an immunogen. You've got different kinds of antigens. You've got like pollen, bacteria, fungi, you know, like mushrooms, I guess, and like different sort of things like that, viruses, and, you know, dust could be an antigen. Now, dust coming into your system, you breathe in some dust, you don't instantly get ill or start trying to fight the dust, because, you know, it's just dust. Your body's like,
it's not,
you know,
not too
I'm
harmful
okay with this one. But if you've got an allergy to dust or an allergy to pollen, you suddenly have hay fever, or you could go into anaphylactic shock, because your body's like, oh, here's an antigen, here's an immune response, and it goes too much. And that's what an allergy is. It's literally just an immune response to an antigen that is generally fine. It's not going to hurt you too much. When an antigen, like I said, so what an antigens basically are recognized by your body because of the way that they've got sort of chemicals on their surface. Usually it's proteins. They bind to sort of specific cells in your immune system, and that's how they recognize cells. So that's how this happens. Basically, it's chemicals that are on the surface, molecules that are on the surface of the antigen, and the surface of your body cells. They can bind to each other, and that's how you recognize things. Does that make sense to you?
Yeah, it's like a little key in a lock.
Kind of, yeah.
Okay.
So if the key fits the lock, your body's like, well, you're going down. Sorry, buddy. Or sometimes it's not. Sometimes it's like if the key fits the lock, it's like, okay, you're not from around here, but you can pass because you're dust. So
it's like a bouncer checking ID. It's like, you can come in, mate.
Exactly.
Nah, that's a fake ID.
Exactly, but it's got to check. It checks everyone's ID, you know, but it only refuses some people. Other people, it can just let in.
Okay.
And I'm not even
tyrannical
going to say that.
bouncer.
So there are specific types of. There's a specific type of white blood cell called a B lymphocyte, or B cells, and they produce antibodies. And antibodies basically can recognize these antigens, and each antibody is specific to an antigen. So basically, there's like antibodies are very specific.
Okay.
In that one type of antibody, like one particular antibody, is specific to this antigen, but it can't recognize another one.
Okay.
And basically, antibodies stay in your body. It could take a few days for them to develop, but after you're first exposed to something, your immune system will then recognize that thing and defend against it. So that's the key point. That's the great thing about antibodies. So you've got these things called memory cells, which basically just kind of remember all of the things you come into contact with. And
that's very helpful.
It's very good, very good. So it remembers all the things that you've come into contact with, and if you come into contact with it again, it will produce those antibodies for that specific thing, which is great.
I see.
So what antibodies do is, like, remember how I said they recognize things by sort of binding to molecules on the surface.
Yes.
Yeah. Basically, what antibodies do is they bind to the surface of the antigen, and then they basically, when something comes into your body, the antibodies can bind to the surface of the entirety of the thing. So it can basically cover the entire surface of the antigen. And at that point, it basically stops it from doing what it needs to do. Because either binding will change the sort of structure of it to the point that it's unable to be sort of pathogenic or dangerous, or it couldn't not move around like it's supposed to, or it could just make it ready to be digested by a phagocyte, which we've talked about already. The things that swallow. Like, look, there you go. You were doing that, weren't you?
Sorry, I was. It's been a long day. I've been dealing with tax problems. I'm tired.
He was imitating a phagocyte. That's what they do.
Sorry.
That's kind of how antibodies work. And you can maybe already kind of tell how we use vaccines based on this. Bear in mind, like I said, it takes antibodies a few days to be produced in the body, and they can stay in the body. But once they've kind of been produced, they can stay in circulation for a few months after infection. So if you get infected by something, you've got the antibodies in your system for a few months afterwards. But then you've also got the memory cells, which stick around longer than that. And what they basically do is they store sort of information. They're basically able to recognize an antigen whenever it sort of comes back again. And they confer a secondary immune response. And that secondary immune response is much quicker and stronger than the primary response, obviously, because you've already got the antibodies, the sort of plan for the antibodies for it. And it just sort of, it bangs them out, it knocks them out real quick. And it's like, I know how to do this. It's like doing a test that you've already done.
Right.
So that's secondary. The secondary meaning the first ones are the ones that go and eat.
No. So secondary as in for the second time.
Okay. Oh, okay. Fine.
Oh,
yeah.
Okay.
So the first time you get infected, and you'll probably get ill, right? Because your body's got to spend time making antibodies for it and figuring out how to fight this thing. And then the second time, you've got your memory cells that are like, hey, I remember this.
We've been here before.
Exactly. So you probably won't get ill because.
So that's what's meant by secondary immune response. Is it's the second exposure to an illness, not like you've got your front line and your secondary defenses.
Yeah.
Wow.
Yeah. So
I didn't know that.
So it takes that's from the source that I've used, which you can find in the description. That's what it was referring to. But yeah, it takes a smaller stimulus and it can happen a lot quicker. And that smaller stimulus can come years even after the first exposure to the sort of disease, or to the antigen rather. And yeah, so this basically protects you from lots of different things. It protects you from parasites, viruses, bacteria, fungi, loads of different things. And obviously, this sort of misfiring is what causes autoimmune diseases or autoimmune disorders. And it's also really important for vaccine therapy because that's what we use. That's the system that we use. And you might be asking yourself, okay, well, if we have like sort of memory, and we shouldn't really be getting ill from the same thing more than once, then why do we get the cold so often? Or why can you get pneumonia more than once? Or why can you get diarrhea often?
He shape shifts.
Well, so the thing is that what we do is we say the cold is something, diarrhea is in it, like the cold is an illness, diarrhea is an illness, and pneumonia is an illness. When really they're more a collection of symptoms, and they could be caused by. So, for example, the common cold can be caused by over 200 viruses. It can cause the common cold, like symptoms of the common cold.
So every time you get a cold, you're technically getting a different virus.
Yeah.
Giving you the same symptoms.
So that's why when you're like, oh well, why can't we just make a vaccine for the common cold? We could for one of them, and then another one,
and then you've got the hundreds of other ones,
and then also because there's so many of them, they're changing quite often, and that's why you need to constantly get flu vaccines because there's a new flu virus popping up. Like basically every year they're making new vaccines for the flu because it's quite variable.
Yeah.
So that's why you can get ill with things. That's why you can get ill with some things multiple times because even though you've got the memory cells for one thing, something very similar won't trigger the same response because won't necessarily trigger the same response because it's not the same thing.
Right.
Yeah? Good. So we're now going to go over what types of vaccine there are, and dear Lord, there are a few. So stick in.
Oh, how many?
About I guess 4.
Okay.
That's manageable.
All right. I think we can pay attention for 4.
So, right.
Maybe.
So the first type is whole pathogen vaccines. you can probably understand what's in these. It's the whole pathogen.
That's the thing I was saying.
Wow.
It's the dead thing that you put in your veins.
So there's two sort of subtypes of this. There's live vaccines. There's live attenuated vaccines and killed vaccines. So killed ones, they're very easy. You just take an entire pathogen, you kill it using either heat or sort of radiation or anything, so that they can't cause a disease because it's dead. And essentially, what you do is you just chuck it into a body. You inject it in, or however you want to deliver it in. You get it in there, and your body's like,
straw.
I recognize you. I recognize you. I'm going to beat you up. So no, basically, the reason that this works is because, like we said already, it's the outside, the molecules on the outside of a sort of the molecules on the outside of a sort of invader that your body recognizes. So it doesn't matter if the inside of that invader is dead, so long as the outside stays the same.
It doesn't matter if it's dead as long as what?
The outside stays the same.
The outside stays the same. So that's like, it doesn't matter if the contents of your castle are dead, as long as the keyholes are the same keyholes.
As long as the structure is the same?
I'd recognize you whether you were alive or dead.
Yes.
Yeah?
Yes. Doesn't matter if my heart is beating.
Yeah.
I have the same shell.
That's irrelevant to my assessment of what is Luke. His heart beating is irrelevant.
What? That's messed up, man.
What? No. I mean, you'd still be
You've never experienced me dead. You might hate it.
Oh, I probably wouldn't enjoy it.
Whoa, what a lovely compliment, Corey. Thank you.
Although, don't knock it till you've tried it. That's what I always say. So we'll see.
Could be quite lovely.
Some nice peace and quiet, I think. That'd do me good.
I've played dead on this podcast before, Corey. I'll do it again.
Do it. Very good.
Oh, don't do it. We had to resurrect him last time.
Yeah, I know, but we've got cameras this time, so he has to do it on camera. Not every but the issue with killed ones, and you'd probably be asking yourself, well, why can't we just kill everything and then use that? The issue with this is that not every single disease-causing microbe can be used in this way. You can't just kill something and put it in someone's body. That won't necessarily work every single time. One example of a vaccine that is dead vaccine is the hepatitis A virus. That is a sort of killed virus. So you can do that with chemicals, heat, or radiation. And then there's live attenuated, and these are probably the ones that people start making sound quite scary, because they are live viruses, and they're not dangerous because we've attenuated. They're attenuated. They've been made they've been disabled in their ability to, hurt you. Okay, so it's if the example right beforehand was with the killed ones is I could recognize Luke whether he's alive or dead because I look at his face and I see Luke.
Can we resurrect him? Can we resurrect him?
Oh, well, we'll resurrect him now.
It's not the
Boom,
same.
he's resurrected.
Wow, thank you.
That was so easy.
Now, if Luke's ability to do the podcast was removed from him, he was alive, his ability to do the podcast was removed from him because he lost his voice.
Oh, he had no mouth.
No, because that's a part of his face. He lost his voice. I would still recognize him as Luke, even though his he wasn't able to do his thing. And that's what live attenuated viruses are, or live attenuated vaccines are, rather. There's something that looks the same on the outside because that's how we recognize it with our bodies. But their ability to sort of harm you is taken away. So you could do that either by sort of growing them. I think one of them, they grew it in chickens until it was very good at living in a chicken cell, but it could not live in a person cell, a human cell. So I think there was another one where it was a strain of bacteria that they used. They sort of started making it live at lower and lower temperatures to the point where it couldn't survive in the warmer temperatures of human lungs. So there you go. And then you can just inject that into someone and you know that it won't be able to sort of reproduce enough to cause you to get really ill, but your body will be able to recognize it and take care of it.
Out of interest, can you do this with viruses because they're not strictly alive?
What you can do with a virus is you could just you just take away its ability to do what it needs to do. So it's not sort of it's not dead, it's not destroyed.
Right.
It's just it can still potentially replicate. It just can't harm you. Do you know what I mean?
But it still needs to be close enough to the original one that it looks the same on the outside.
Yeah.
And so that you train the immune system.
Yeah. basically. Yeah. So these are apparently these could be really easy to create for certain viruses, but difficult to make for more complicated things like bacteria and parasites. And they give you a really strong immune response, and after 2 doses, like 1 or 2 doses, you can have a lifelong immunity. Although the issue with this is that in some cases they can turn back into the scary death form, like what happened. It happened with polio once, and so
in one person,
no,
or one batch, or one country.
No, it's not a batch. It's not
one planet.
As in you inject it into a person, and it becomes it sort of reverts back to the wild type, the dangerous type. And that happened. I mean, that happened with polio, and quite a few people got. We spoke about this before. Quite a few people got polio from that vaccine because it started acting like the real thing. But to be fair,
they okay?
No, they had polio. Luke.
Oh,
there's a reason we vaccinate against polio, because you're not okay if you get polio. But the good news is obviously that even if this were to happen a couple times, the alternative is everyone gets polio.
True.
So. Yeah, and to be fair, this doesn't happen. It's not like this happens often. It's just something you need to be aware of. And if it's likely to happen with, whatever sort of the virus that you're using, then you will use another route. You won't use this option.
Right.
So that's just one way we do it. Those were kind of the sort of starting ways. Those were the first kind of vaccines that we made. And then you've got subunit vaccines. So instead of having the entire pathogen, the entire thing, you just use a little part of it. And and obviously this makes sense if you remember that it's only molecules on the outside that are recognized. So basically you just need to get enough of what is recognized. So put it this way, when you've got a key, let's say you've got a whole key, right? You've got a whole bloody key.
A really big key.
A really big key. You just chop off the end of it, but the bit that goes into the lock is still there. Or in Luke's case, you can chop off his head and I'd still recognize him as Luke, even though he's got no body. Because his face is what I recognize.
One of a
kind.
kind.
Am being mutilated today.
You've been killed, resurrected.
Lost my voice, had my head chopped off. What's next?
What's next
the
in
other
the world
type of
Luke?
vaccine that you're going to do with me?
I don't really know how I'm going to fit you to the examples of the next ones, but we'll find a way. No, so subunit vaccines. This can make them obviously this could be safer and easier to produce, but you need something called adjuvants, basically to make it a little more potent. Because while it can produce an immune response, it might not be quite as strong protection as live, attenuated, or killed vaccines.
Right.
So yeah, these are much safer, but also not as much of a. There's less of a risk, but less of a reward, basically. And yeah, but the great part of it as well is that if you only have the bits that you need for an immune response, as in if you only have the antigen, really, you can have fewer side effects. So obviously, some vaccines can come with some side effects, sort of fever, swelling, itchiness, things like that. Really, when put in on the grand scale of things, there aren't that many side effects, and the number of people they affect it's such a small number that it's well worth being vaccinated. Don't let this scare you off of vaccines. But you can minimize those side effects if you just use the essential antigen that your body needs to recognize. And there's also another type. There's other types of subunit vaccines. So one type is polysaccharide. That just basically means sugar. So bacteria can have sugar on the outside of them. That's just there. And essentially, if you use this sugar, your body can recognize that, and it's like, that's bacteria because it's sugar. But actually, it's not the whole bacteria. It's just the sugar that's on the outside of the bacteria. We use that for the Haemophilus influenza type B, the Hib virus, the Hib vaccine. And yeah, so initially we did it with just the sort of sugar, but it didn't work quite as well. So now we use it. We basically attach it to a protein antigen, which makes it sort of more protective. So you can use basically sugar plus protein. That could be one of the subunits. There's also toxoids, which they prevent against bacterial illnesses like diphtheria or tetanus, and they basically they can recognize the toxins that are secreted by the bacteria. So instead of recognizing the bacteria itself, these ones recognize the toxins, and what you do is you give it basically a part of the toxin and chemically inactivate them. You give someone a part of the toxin, chemically inactivate it, and your body develops an immune response to that. Yeah.
Right.
So what we've gone over so far are killed ones, which is just dead vaccine.
Yeah.
Live attenuated, which are live ones but they're not able to do the thing that they're supposed to do. Subunit vaccines, which are just a part of the sort of the pathogen, just the part that you're going to recognize. And of the sort of subunits, there's toxoids and polysaccharide, which is just sugar and toxin, basically. So we've also got recombinant protein ones, recombinant protein vaccines, which essentially you take. So recombinant just means basically recombination, just putting together in different ways, or putting together putting together again, which basically you can take DNA from 2 or more places and combine it. And so the hepatitis B vaccine, that's a recombinant protein vaccine. Basically, a recombinant protein, bear in mind, is a protein that's made from different sources of DNA. Because DNA codes proteins, basically. So if you bring in together different sources of DNA, you can make a slightly different protein. So the hepatitis B vaccine is a recombinant protein vaccine. And it's the antigen is the hepatitis B virus protein that's on the outside of it, but it's produced by yeast cells. And in the yeast cells, you've put basically what happens is they put the DNA code for the protein that's on the outside of the hepatitis B virus.
Right.
They put that DNA into yeast cells. You make the yeast cells make it. So the yeast cells have got that protein on the outside of them, and you inject someone with this yeast, and they're like, your body's like, hepatitis B? Hepatitis C a year later, and it's actually just yeast. And so when your body comes in contact with hepatitis B, you're like, it's like, haha, I know what to do here. Yes.
So that's like dressing me up dressing someone else up in a Luke costume.
That's like, yeah.
So that they could recognize the real Luke when he comes in.
Yeah.
Wow.
But they didn't have to really meet me.
So yeah, we get a Luke mask and we just put it on someone, and your body's like, that is Luke. That is 100% Luke, and I know what to do when I see Luke now.
I know not to let you in now.
I have a question.
Yes.
So, if you just put some yeast into your body, your body would react to that in a very bad way, correct?
What do you mean?
So your body would try and fight yeast if it was in your
depends.
body.
Yes, probably. Well,
Okay. So what I don't understand is, okay, so let's give the example of the last type that you've just described, right? So you'd get someone, you get like basically someone, so imagine I'm really, really scary, and you get someone really not scary, and you dress them up in a Luke costume so that someone can be like, okay, that's what Luke looks like, and then they fight the person who looks like me. But then the suggestion is that then they know how to fight me when I turn up. And what if I behave in a different way, or I am just like much more strong than the thing that they practiced on? Like, how does that just because they know what to look for, how does that turn into an ability to fight that thing?
Because knowing what to look for is fighting it. Because like I said, antibodies just, they just attach to the outside of the thing, which either stops it from being able to do what it's supposed to do, or stops it from moving, or just makes it easier to be digested.
Yeah.
So when I say a specific immune response isn't your body thinking, okay, here's the strategy for how to fight. It's literally just make the antibodies and do what we normally do. It's just antibodies. The antibodies are the specific immune response. But because antibodies are specific, there's like, you can't just throw out any antibody. You've got to throw out the specific antibody for that antigen.
Because they got to stick to the outside.
Yeah.
So yeah, it's a lot less. It's not a lot less of an active warfare going on inside your body than I thought. Where I thought there was like they had to practice different strategies of how to take down this sort of specific invader. Whereas actually, it's more just like when you recognize a certain invader, you just chuck all of your troops at it and they all just grab on, and they know how to grab on. They've practiced grabbing on before, and so they just grab on really well, and then you don't get ill.
But then bear in mind, the antibodies, the thing is that, like I said, antibodies can kind of change the antigen, the sort of pathogen that's coming in, or the immunogen, the thing that causes the immune response. They can change it so that it's unable to do what it's supposed to do. So in that sense, it is very specific. Or they can just swarm it, or they can stop it from moving. There's different things that they can do, and depending on the antibody, that is sort of the antibody and the antigen. Depending on those two, there are different things that can happen to it.
But that's why I'm confused, is because if you're given, like, say, for example, you're given the one that's the part, like the bit where you've chopped my head off and you've shown your immune system my head.
Mm-hmm.
Well, what if my arms fight in a different way and they never see my arms?
That doesn't matter. That's not how it works. Bear in mind, right?
Oh, okay.
All your body.
The scientists give it the part that the immune system needs to see in order to deactivate it.
Yeah, so you're thinking about it way too you're getting way too into the metaphor. When we're talking about you, we're not talking about fighting you, because there's many things you can do.
That's what I'm talking about.
We're just talking about recognizing you, because recognizing you is all we need to be able to do to fight you.
Okay. Right.
Generally.
Cool.
Yeah?
Yeah.
I just want to correct myself there, though. I said that they inject the yeast cells in. No, they just use the yeast. They just use the yeast to produce the hepatitis B vaccine.
Like a virus does.
No. Well, what? No. They just put the DNA for the hepatitis B protein into the yeast, and then the yeast produce the hepatitis B protein for us. We do that all the time.
But that's what a virus does. It puts its DNA into us and then makes us make it.
Yeah, I mean, okay, you could say that. We use that. We do that for lots of things, though.
Look at us talking crap about a specific thing that this virus does, and then doing exactly what it does but to yeast. And who cares? It's just yeast, man. I don't care. It's only yeast. It's not me. I'm more important than yeast.
Luke, do you like bread?
I really like bread, which is why I'm defending yeast.
You're killing yeast to make your bread.
Oh.
Yeah.
Oh no.
Yeah.
I suddenly hate
Hypocrite.
bread.
Yeah. So.
Oh.
Yeah, look at you.
Vegan.
Yeah, not very vegan, is it? Just because you can't see them doesn't mean they're not alive.
Right.
We also use recombinant protein vaccines for things like the HPV vaccine. That's also a recombinant protein antigen. And yeah, so that's kind of that whole sort of area. There's also a sort of newer type called nucleic acid vaccines. Do you guys remember what nucleic acids are?
Yeah, it's what DNA is made up of.
Yeah, so I mean, essentially,
well, it's ribonucleic acid. Yeah.
Yeah. So
deoxy boy.
Right. So this is something that is quite new, nucleic acid vaccines. And so bear in mind, nucleic acid, it could be DNA or RNA. And DNA, we're not really going to talk too much about that. But basically, what DNA and mRNA vaccines do is something beautiful. So remember how we were talking about sort of how viruses use our bodies to make their own sort of proteins and make more viruses, and how we're using our own immune system to fight the viruses using vaccines.
Yeah.
Well, mRNA vaccines take it one step further. Bear in mind, we did an episode on all of this before, so if you want to know in depth, go ahead and watch that. Linked in the description. But all you need to know for this is that mRNA is something. It's a sort of long chain molecule that is important and used for making proteins. So if you put mRNA into a cell, it will make a protein, basically.
Yes.
You'll come into something called a ribosome, and a protein will be produced using that mRNA sort of code. Now, mRNA, it's basically a specific code to make a protein. Just think of it like that. Specific sort of recipe for a protein.
Yeah.
You use it and you put together a specific protein. Now, what we do is we inject that mRNA, or not inject, we put that mRNA into cells, and then they start producing whatever we want it to. So what we want to do is make sort of an mRNA recipe for an antigen. So we pop some mRNA into a cell, and then the cell starts making the antigen, and the cell's like, hey, this is an antigen. And your body's like, yes, it is. I recognize that now. So you're using your own body as the production house for the antigens for your body to recognize, for it to produce an immune response.
Wow.
Which is just fantastic. And the great part about mRNA is that it's short-lived. It's not going to last a long time, so it's not it's less likely to make you ill. And you can have, what you can do with it as well is you can put in things that viruses use to sort of self-replicate the mRNA, so that it continues to produce more antigens if you need it to be a little more potent. But again, it's not going to be super long-lived. So you just use your body as a little production house, which is fantastic. Which is, I think, I think mRNA vaccines might be what they're trying to do for the current situation vaccine.
Oh.
but only time will tell.
What are the benefits of doing it that way?
Well,
in what situations would you use an mRNA vaccine?
The thing is that they're quicker and easier to produce. And all you need to produce it is an mRNA, sort of the code.
Yeah.
And you can get that code for the protein just by sort of basically finding out what the code of the protein is.
Right.
Which you just need to decode the protein basically. So if you've got an antigen that's on the outside of a virus, let's say, which is just a protein that your body recognizes, all you need to do is be like, okay, this is a protein that the body will recognize. Let's find the code for that protein, which is not too difficult of a process. And then make that code. Boom, you make that code. Fairly easy. And you just use that template to make more mRNA, more of the code. It's basically all you need to do, right? If we use the sort of recipe thing again, what is happening with this is the antigen is a lovely meal, okay? You go to a restaurant, you have the lovely meal, you're like, it's a pretty good meal. I want to make that at home. So you go home and you sort of you figure out what the recipe for that meal is.
Yep.
You're like, okay, I had this and that in it, very good. Okay, I've got the recipe for it. Then you photocopy that recipe and you give it to all of your friends. Now all of your friends are able to make that recipe, and that's essentially what's happening with the mRNA vaccines. And yeah, they're easier to produce because you just need to get that sort of code, and we've already got all the sort of apparatus to produce mRNA vaccines, technically, because we for research produce mRNA a lot. Obviously, we'd need to scale it up. Some things are a bit costly right now, and there are barriers. But it is promising. It is sort of cutting edge right now. That's where we're looking for vaccines. And also, the great thing about mRNA vaccines is that they can also be used against things like cancers and non-infectious diseases, which is just fantastic.
Yeah.
So another downside of the mRNA vaccines, though, is that we're still having trouble trying to figure out how we get them into the cell. That's sort of the perfect delivery method. How do we get it in there and make sure that it's going to sort of do its job? That's kind of what we're trying to figure out right now. We've obviously, this is the thing. This is not well established. It's not like there are loads of mRNA vaccines out right now. This is something that we're developing and we're working on. But we're getting there, and it could be the future of vaccinations potentially. But that is sort of the overview on vaccines. So you've got your subunit vaccines, your whole pathogen vaccines. Those are the killed and live attenuated ones.
Yep.
You've got your nucleic acid vaccines, and I think that's all the ones that I covered, isn't it? It is. Yeah. So it's just basically those types, and they're broken out into subtypes. But that's really what you need to remember. It's all of these different ways of getting something for your body to recognize into your body without harming it.
That's the aim.
That is it. That is the aim. So there's also we've got to talk about we know what vaccines are, right? We know what they are.
Yeah.
We know what they do. We know how they work.
We do.
We need to figure out how we can start making them. And how we start making them is obviously we've got to figure out which kind of vaccine we want to use and all of that stuff. But we also need to test them, basically.
Right.
Do you know what I mean? Before we can start large scale production, we've got to test that they sort of work.
Make sure they're effective.
Yeah. So it could take 10 to 15 years for a vaccine to be produced. That's not abnormal. In fact, I think the fastest vaccine to be produced up until recently was, I think it was maybe about 4 years. I can't remember which one for. But it could take a while for vaccines to be produced. And there are some reasons for that. So mostly it's because of the sort of rigorous it's because of the rigorous testing. It's because of the rigorous testing and funding. So it takes a lot of money to do all of these sort of tests and funding, and there's a lot of different hoops you need to jump through. And if you're worried right now about a vaccine coming out quite quickly, bear in mind that that's not the case. It's not because they've skipped safety steps. It's because it costs a lot of money to go into each stage and to have it regulated and sort of checked. And there is a lot of money going into the virus for the current situation.
That's true.
So when you're if you're going the private route, you've got the company. So if you're going the private route or the sort of public route, so there's the academic route and the private route for making vaccines. Academic, you need to get funding grants from different places, and that can take a while, to get funding. And if you're going the professional route, sort of private route, that's basically a company doing it. And if a company is going to do it, it needs to be profitable and they need to not be wasting their money. And so they're very careful about what they do. Is there's a slow process to check and make sure that if we go to the next step, we won't be losing money.
Yeah.
And what's happening right now is you're basically seeing what happens when the sort of FDA is like, okay, you guys are fast tracked to being, you're put at the top of the list, right? We're not like, we've kind of checked, we're happy with this. Okay, go ahead and make it. Okay, we don't really worry about wasting too much money because we need to get this out now.
Yeah.
Go ahead and do that. So all of these sort of slow parts are kind of being cut as short as they can. And the parts that take longer, like actually trying to find something, trying to find a vaccine, as in trying to find the antigen to use and a safe way to get it delivered, all of that stuff, that takes as long as it takes. That wasn't really sped up. There's also the testing of it, as in the sort of safety the trials and testing the safety of it. That's not really sped up either, because you need to do those. The only thing that you wouldn't know is the sort of super long, like the quite long-term effect of how effective will it be in 5 years or 1 year or 2 years, because we don't have 5 years to do it. But ultimately, we have a fair idea. We'll have a fair idea of how safe everything is, and we're not really skipping too many steps to get it out in 18 months. We're just skipping all of the waiting around, twiddling your thumbs, looking for money kind of steps.
Yeah, I'd read that a lot, because what we're trying to sort of assuage some of the fears that come from the fact that we heard so early on, like the fastest we've ever developed a vaccine is 4 years, or it's going to take years to do this, and then suddenly it's like, oh, it's been less than a year and we think we're there. I read that one of the reasons why they were able to go so quickly in this instance was that in the past you had to sort of do all the steps that Corey's talked about, where you had to like get a vaccine, so get a pathogen, and then you had to weaken it, and you had to figure out how to weaken it in the right way. And now you can start developing a vaccine with just the DNA sequence. And that is like so much faster than it used to be.
Mm-hmm. And also like the actual production, again, the sort of production of the other vaccines, you need to sort of culture these things and kill them and make sure that they're safe for there's so many different steps you need to go through, whereas producing high quality mRNA is quite quick. So there are a lot of reasons that we can make a vaccine faster than normal right now. And I can say with sort of the utmost certainty that one of those reasons is not because we are throwing safety concerns out of the window. There is absolutely no way that people will be giving out an entirely unsafe vaccine. That's just not something that would happen in a situation like this. And in fact, we've seen during other pandemics sort of how things are dealt with, and we're not still worried about sort of swine flu, because we're not still worried about swine flu sort of thing. So if you're worried about a vaccine, I would really say don't be too worried. The tests have been done, and the longer it takes between now and the vaccine actually coming out is just more time to see how long it lasts and how effective it is. So vaccine testing, like I said, it takes 10 to 15 years for a vaccine to be produced, sort of thing, because it needs to go through lots of rigorous testing. But a lot of that time is taken up by securing funding and waiting for regulatory bodies to sort of get things done. It's like, okay, put it this way. You send away your what's it called? Driving license. You've got to send it away. You've got to send away your form. You've got to it takes like 3 weeks. They send it back to you and you're like, okay, good, great. How long does it take for someone to check that form and print out a driving license? Do you know how long it actually takes? It takes about half an hour at most, because you can get it done. You can get like passports. You can get a passport done in like 30 minutes. If you really need to get one done in 30 minutes, you can pay hundreds of pounds to get it done in 30 minutes. Yeah. Or you could pay the £30 that it takes to get it done in like a month or whatever. That's what we're doing here. We're just cutting out all of the sort of bureaucratic steps and waiting for money and all of this and that to get people to sort of do things as quickly as sort of the regulatory bodies to do things as quickly as they can to process sort of all of that stuff. But the actual safety, it's not really going to be compromised. And the thing about vaccines is that they are very rigorously tested to the point that if you're ever worried about any vaccine, you shouldn't be, because they are tested very strictly. So I'll just briefly go through all the stages of a vaccine being produced, and then I'll be sort of more specific about some particular stages. So there's the literature review, which is basically just looking at all of the stuff that's been done before, and seeing what's going on there. And then you've got the theoretical development or the innovation, basically coming up with the new idea or changing an existing idea to sort of produce a new vaccine. And then the lab testing and development, that's in vitro, in glass testing, basically just doing things in test tubes using individual cells, and then in vivo testing using sort of mice. So basically what we're doing there is testing the sort of the idea for the vaccine in a test tube with single cells, and then moving up to testing it in mice. In that way, usually it's with mice. And it's already at that stage got to pass a lot of safety tests, and it's got to show that it works in animals. So before you can even progress on to sort of working on people, you need to do it on sort of individual cells and then animals, and prove that it's safe and works in both of those. And bear in mind, at all of these stages, and this is what they taught me in uni, in all of these stages, when you get to the end of it, there's a very intense review of, is it worth going forward on this? It's basically like a business, Before you make any sort of big business step or venture, there are risks there are sort of risks you need to take and rewards that may come from those risks. Now, you need to make damn sure that when you're making a risk, you are not going to lose, especially if you're working for a company that does not want to just waste its money sort of pissing away on a vaccine that doesn't work.
Yeah.
So at the end of all of these stages, you review it very intensely, and you think, okay, we're going to go ahead with it. We're going to go ahead with it. So lab testing, once it's safe in animals, you then move on to phase 1 study, and that's an initial trial with a small group of adults, usually up to 100 people. And you basically just do that. You figure out whether there's any major that's the safety concerns for humans, and you also figure out generally what the most effective dose is. And then you've got phase 2 study. Once you know that it's safe for humans, you've got a decent idea of what dose you want to use. That's a bigger group of people you test it in, a few hundred people. Those basically check that it works consistently, and they look at whether it generates an immune response. And you also start looking for side effects. You just start looking sort of more at side effects at this stage, because there can be some side effects of vaccines, like we said, fever and things like that.
Yeah.
Then phase 3 study, then you use an even bigger group of people, and you get a lot of data on the sort of safety of the vaccine and the efficacy. Efficacy is how well something works.
Yeah.
And that means that basically you can sort of look to see if the vaccine works to the point that it needs to sort of prevent people from getting the disease, and actually reduce like case numbers, and you get an even better view of potential side effects than you had initially. You go up by a lot each time here. So you start off with about 100 people, then you can have quite a few hundred people, and then you've got a few thousand people. So at each stage, you're getting more and more data, and that gives you a more and more accurate picture of how well your vaccine works. So once you've passed phase 3, you've got licensing, which is a review of all of the data. And this is for the UK, by the way, so it'd be the UK government. And this is by experts. So experts in the UK government, basically UK government experts review this data from the entire study, and they decide whether or not they want to allow it to sort of go ahead. So this is done through the Medicines and Healthcare Products Regulatory Agency, MHRA, or the not anymore, but the European Medicines Agency, the EMA. It's probably going to change very soon. And they check that the product meets the necessary like effectiveness and safety levels, and they make sure that the advantages outweigh the disadvantages. So bear in mind, if you've got a company producing the vaccine, it's not the company that's deciding whether or not they're allowed to make that vaccine. There is a sort of separate body that specifically decides whether or not vaccines are safe enough to be used. And then at that point, you've got phase 4 studies, and that's after that's after marketing. That's surveillance to make sure that the side effects of the vaccine, there aren't any sort of more worse side effects of the vaccine, and that the vaccine continues to be effective. And those could either be requested by the regulatory body or carried out by the pharmaceutical industry. So basically, even once you've got your vaccine made and out to market, you have not finished testing it, you continue to monitor it to make sure that it's still safe. Which, I mean, at that point, they're like, if there are, and things can be modified slightly, they can have different advice, and in very, very vastly small number of cases, they may recall it. I can't even think off the top of my head of a time that's happened. It has happened, I'm fairly sure, but I can't think of a time off the top of my head that's happened. But that is a potential outcome because they are continuously making sure that this vaccine is safe. Even to the point where they're like, okay, it's safe enough for people to use, but let's just make double extra sure.
Yeah.
So we're very sure that vaccines are safe. Usually once they're out amongst the people, and if they're not safe, we'll know about it as quickly as possible because we're keeping an eye on it, and that's an overview of those stages.
Nice.
Yeah. So let's just sort of remind you of what we went over. We went over all of the different sort of stages that go into making a vaccine. Now we're going to go into specifically phase 1, 2, and 3 of testing, or rather phase 1, 2, and 3 of trials. We're just going to go over like specifically what those are all about. So phase 1, the objective of phase 1 is to bring together the Avengers. But on top of that, it's, as you remember, it was the part where we sort of had about 100 people. The main objective of this is to just kind of figure out how safe it is. We've already done our animal studies. We want to see how safe it is in humans. And then we also want to get an immune response and really figure out what that is. And the dose, the sort of schedule of the vaccines, how often you take them, how far apart the doses are, and how you get the vaccine into people is also sort of figured out at this stage. This is where you look at that. And the study population, so you've got small populations of healthy people who are, it says here immunocompetent. That just means people who have an immune system that does a good job.
Yay.
It's good. You're working all right, buddy. Yeah, you deserve a pat on the back there. No, pat on the back.
You're competent.
I don't like that though, because then the alternative is quite rude.
Incompetent.
Yeah, it's because it's quite then rude to the people that are immunocompromised, which is through no fault of their own.
Yeah.
So it's got some immunocompetent adults, and they've got to be at a low risk of getting an infection that is relevant to the vaccine. And that looks at like sort of exposure history, travel, all of that different kind of stuff. And then so based on the results of adult studies, which you can call 1A, you can then do 1B of sort of people in different sort of age or population groups, which are more closer to the population you're going to be giving this vaccination to. So let me just say that again so it makes more sense. You've got phase 1A, where you do it in a very specific set of adults in a very specific place that are really unlikely to get an infection that is relevant to the vaccine. And then in phase 1B, you can, maybe hone in a little more. Oh, we're going to give this vaccine to 20-year-old women. Let's maybe let's get closer to 20-year-old women there. And that's the people that you use. So then the design of it, you basically, usually they're non-randomized, they're open label, but you can do randomized control trials where you give people a vaccine. A vaccine against a different disease or a placebo. So usually with these trials, you just do them open. You're just like, okay, let's just not randomize them. Let's just give these people this thing, see if it generally works. You can also do it randomized and controlled. A randomized control with a placebo or a different vaccine.
Why would you not do it double blind?
So you can do it single blinded or double blinded, and the reason that you may want to do a slightly more open or without controls or without the sort of randomized controls is because you want to have a very specific group of people try it in a very specific geography. Okay, so also what they could do is they could have sort of bedside formulations, which basically just means you can sort of mix the antigen and the adjuvant. I did not look up how to say this word. Basically, it's the part that can make the vaccine more potent. So you can mix the antigen and the adjuvant just before putting it into the person. And that basically allows you to try lots of different sort of combinations of antigens and adjuvants. So if you've got an antigen, you're like, okay, we need to figure out what else to add to it to make it a little more, add a little more spice, give it a little more strength. You can try lots of different things by mixing it sort of just before you sort of inoculate someone with it. And that means you don't need to have too many vaccine formulations. And then that's phase 1 done. So you've done that. You've figured out, okay, immune response, good. Not too unsafe. People are generally fine. Phase 2. So the objective of phase 2 is to identify the preparation of the vaccine, the optimal dose, and the schedule to be taken up for the phase 3 trials. So these studies are, because of the sample size, they're bigger than phase 1 studies. They're actually pretty good for telling you how safe and effective it is, the vaccine. So that's pretty good there. And then you also have more variables involved in this one. So age, ethnicity, gender, all of those sort of things can come into this because you can have a wider group of people for phase 2 testing, whereas phase 1 was just a very small sort of subset of adults who probably couldn't get the sort of disease. You can broaden it up for phase 2 trials. And another objective of this is to also find the age of first administration of the vaccine. So at what age are we going to give it to people first, the number of doses of the vaccine, and like I said, the time between the vaccine dose. The population, the people that you do the study on, you do it on like sort of you can do it on people from lots of different places. So loads of different populations, and you could have adults, teenagers, kids, even babies or pregnant women. But usually with babies, what you do is something called a stepped-out approach, where you start with adults, then you do teenagers, then you do kids, and then you finally move on to sort of infants once you're sure that it's safe enough. And bear in mind, when I say phase 1, phase 2, phase 3, this isn't just sort of one single test that is done. There are sort of multiple stages within each sort of phase. Much like with each phase of Marvel movies, there are multiple Marvel movies. So in terms of the study design, in randomized control designs, the vaccine is tested against a placebo or another vaccine. And they're usually done, where controlled trials are feasible, is where you can kind of have a good amount of information about the population, about like the sort of sex ratio, migration, disease patterns, and you can have good information about the disease that you're sort of looking at, the different strains that are there, the severity and the pattern, the seasonality. You basically will try and do those sort of randomized control studies in a place where all of that information is quite readily available. So basically, if let's say you want to do a vaccine for this virus called hand virus. That's the first thing that came to mind. If you want to do a trial,
crippling to the hands.
Trial for the hand virus, but you know that you don't have much information on the hand virus in the south of England, but you've got loads of information on it in Scotland, and also you've got a lot of information on the people of Scotland. You're probably going to test in Scotland rather than the south of England.
Yeah.
So that's phase 2 over. You've met all of your objectives there. You know the dosage. You know when your sort of dose pattern. You know how safe it is. You move on to phase 3. Now these trials are important because these are the last ones before you can move on to sort of registration to be approved to go to market, and these are effectively the sort of last go, the final formulation, and they're specifically designed to figure out very, very, very specifically the efficacy and the safety, and you might have heard this already. Vaccine efficacy, you calculate it. There's a specific way to calculate it. So it's the incidence of the disease in the unvaccinated population minus the incidence of the disease in the vaccinated population over the incidence of the disease in the unvaccinated population. Basically, if you think about it, it's like unvaccinated minus vaccinated all over unvaccinated times 100. That basically gets you a percentage. So it's a percentage in the difference of the number of people that get the disease, basically.
Yeah.
So if you put it this way, 95% would probably mean that you've got 95% of people who get vaccinated will not get the virus.
Right.
Basically. In comparison to people who are
unvaccinated.
In comparison to unvaccinated. You want to really figure out, at the end of this, you really want to figure out how prevalent the disease is amongst the vaccinated. sort of how many people get the infection and how well protected they are. That's what you want to figure out by the end of this. The people that you use in phase 3 trials are lots of different people. These are huge trials, thousands and thousands of people from the target population. So if your target population is little girls, you have thousands of little girls that you're just shooting up with your phase 3 vaccine test, and you want to give them, you basically do them in this is field conditions. So the previous ones were a little more controlled, because you really want to avoid people coming into contact with certain things, especially if it's sort of a live attenuated virus, which could potentially have an effect on other people. So at this point, you're fairly sure that it's safe. So you do it in more sort of wild type, sort of wild environments, more sort of in the field, as in you would give them at this sort of schedule they would normally be given at when you sort of go to market, and you kind of let them generally go about what they would normally do. So obviously the incidence of the disease in the study population impacts the sample size, by which I mean, if you've got a really low incidence of the disease, you need more people, because otherwise you won't necessarily have enough data.
Less accurate.
Yeah, less accurate, exactly. And so that's about the population. You've got a lot of people, and you try and be really specific about who you're, the group that you want to target. And then in terms of the design, you would do a randomized control trial, and you'd use either a placebo, a different vaccine, or nothing in this case. And so from this, you get a pretty good idea of long-term protection and whether you need a booster vaccination to follow the initial ones. So at this point, you can't necessarily answer everything with one study, but you can get a pretty good idea of what it's going to be like when it goes to market. And so with multiple studies, you'll do it under different conditions with different sort of disease patterns and populations. So by the end of phase 3, you've got a really good idea of how your vaccine is going to work when you actually ship it out to go to sort of the general population. And once you've done that, once you've got it through all the trials, you've got to meet all the regulations that are set out. And there are different authorities that have to sort of agree to this. The International Conference on Harmonization of Good Clinical Practice. There's the Declaration of Helsinki. There's the EU Clinical Trials Directive. There's the RCPCH guidelines for the ethical conduct of medical research involving children. And also in the UK, it's got to pass an NHS Research Ethics Committee, the local research NHS Research and Development Office, and the Health and Safety Executive for certain types of trials. So there's loads of different sort of regulatory bodies that regulate these sort of things. And when you get it before you even sort of get it to market, it's got to go through so many different regulation processes. And as we've said already, these are the parts that are being sort of sped up in terms of if it usually takes 3 weeks to get something onto their desk and for them to look through all the things, you're basically saying no, you read it now.
This is kind of world news.
You read it now. Yeah, exactly.
Kind of fast track it.
Exactly.
Yeah.
Again, think of your passport. You can fast track a passport, but it doesn't mean that you've got a worse passport. It just means they've not sat around doing whatever passport people do up until that point. And so then it's monitored once it's already gone out. Like we said, there's monitoring. So they're tested they're tested a lot before they're even allowed to go into the market. And then once they're out, they're being tested still. That's done by the Medicines Healthcare Products Regulatory Agency, which we mentioned before. And basically, if there are suspected side effects, those are sent to the MHRA by drug companies, and they have to pass on any reports of suspected side effects that are defined as serious. And since 2005, patients themselves can do that, and then also health professionals can do that as well. So it's not just drug companies you need to trust to send that information. It can be drug companies, health professionals, and patients sending reports of potential side effects to this regulatory sort of committee. And once they've got that, they evaluate it every week. The side effects are compared against the expected side effects, as detailed. There's an information sheet for each vaccine. So the side effects that are reported are compared against the side effects that they've basically got on their information sheet. And if there's an unidentified reaction, or the frequency of reactions is not what they expect, they'll investigate it carefully. Like I said, they can then take action. So what they can do is give out warnings, obviously, and sort of saying, oh, maybe people shouldn't be given this vaccine, or maybe avoid this. And like I said, sometimes they can withdraw the vaccine. And now we just need to cover how vaccines are produced. So, how do you make a vaccine? Different for different kinds of vaccines. So, live attenuated vaccines and dead vaccines are basically made the same way, except at the end of one of them, you kill it. Just like it's like sending a cow to the slaughterhouse. You just you conk that little little virus on its head.
Poor
Can you do that with radiation?
You can do it with radiation, heat, or chemicals.
Radiation is how they get rid of locust testicles that we talked about once on the live show?
Dear Lord.
It was, mosquito testicles.
Yeah.
No, it wasn't. No, it was specifically that they don't do that because the mosquito testicles are too small. Anyway, on with the show.
It would be quite small.
Okay. So you can grow a virus or anything like that in cell culture. You can, but you basically grow them in something called a bioreactor, which is basically a big bowl. Think about like a washing machine. No. Okay, it's like
something called a bioreactor, which is basically a big bowl.
Think like a washing machine.
Yeah.
But instead of washing your clothes, it's growing microorganisms. Yeah, or like basically a big vat. That's what that is.
Yeah.
So
like an ice cream machine, just turning.
Sure. Basically, you can grow viruses in living cells, and just let the virus sort of replicate, and then you've got your virus. You can, like I said, you can have an attenuated virus. Like we said, you could grow it in a chicken cell, or you can grow it in certain conditions, and then you basically just need to you need to get them out of the cells, which is a kind of difficult part in and of itself. Again, this could be a whole episode. And then you need to filter it and make sure that it's safe enough to be injected into people. There aren't any other contaminants in there, because remember, if you're growing it in another cell, you got a whole other kind of cell in there you got to get rid of. And yeah, so if it's live attenuated, you just make sure that it's attenuated before it goes into someone. If it's a dead virus, you kill it. Easy.
Dead.
So the combination bacterial and genetically engineered, it's kind of similar, but what they do is they if it's bacteria, they don't need a host cell to grow, because they are their own cell. They're not like a virus. Viruses need host cells, but bacteria can just grow in a culture. And so what you would do is then sort of a similar sort of process where you either sort of inactivate the bacteria or take out what you need from them. There's lots of it's quite difficult to do this in some cases. There's lots of different ways of doing it, but basically the tactic here is either grow it and kill it, or grow it and take what you need from it. And then there's also, this is really the reason that I want to do this episode, because I want to talk about this, the flu vaccines, which are needed yearly. Now, the most common way to make a flu vaccine is using an egg.
Oh, like a chicken egg.
Like a chicken egg.
Like a chicken egg.
100%
a chicken. Yeah.
Oh, because you grow it in chickens so that they're not very good at fighting humans, but they can fight chickens.
Well, you grow it in an egg.
But you develop it in chickens, you said, in chicken cells.
Oh, that was with one specific kind of vaccine.
This is nothing to do with that. No. We just happen to grow it in chicken eggs.
Well, okay.
Let's do it with the egg
you can use
time.
it to make the killed vaccine, or you can use it to make the live attenuated one. The one that you get injected with, I think, is usually the killed one, and you can have one that you spray up your nose, and that is the weakened one, the attenuated one. But you grow them both in eggs, and the reason for is essentially you need somewhere for it to grow, and so you give them a fertilized hen's egg, and you incubate it for a few days to let the virus.
Fertilized hen's egg? So it's a baby chicken. You don't grow it in an egg. You grow it in a baby chicken.
No. I mean, it's still an egg. Are you saying that chicken life begins at chicken conception?
Let's not get into this debate now.
You mean again, Luke?
It's just a clump of cells in an egg.
Look, pro-life. All I'm saying is that pro-life people should both be vegan and anti-vax. Oh my God, they would be anti-vaxxers. Never mind.
Yeah, but no, vegans.
And vegans are often anti-vax.
Oh. Anti-vax. Vegans have to be anti-vax.
A lot of vegans are anti-vax. No.
Wow.
Okay, let's move on. So you basically inject a hen's egg with a fertilized hen's egg with some virus. You let it sort of grow over a few days, and then you take the fluid that's got the virus in it from the eggs, and you either inactivate it and purify the antigen, or you kill it and then purify it. And this is the way that we do it because it is quick, it is easy, and it's one of the best ways that we've got. It's literally one of the most common ways to do the flu vaccine, because we need a new one every year. Bear in mind, because the flu is changing every year, and so we need to get a new one every year. So there's this whole thing. Did a whole topic on it at uni. It's stuck in my head now. Anyway, let's move on. We've not got much time left. So once you've grown it in your egg and you've sort of taken it out and you've filtered it and you've made sure it's nice and pure and perfect to be injected into a human, that's it. You're done. You then let it go and basically be put into a human. And then you've got the mRNA ones, and we spoke about these being probably better than other vaccines because they're much easier to produce. And they are. Essentially, you need to just, like I said, you can just kind of, you need to find what your protein is, your antigen. Then you need to get the code to make that protein. And then you just need to insert that bit of code into, you need to get that code, sorry. You need to get the code to make that protein. And then you need to basically just replicate that code. You need to get the sort of template and replicate it up. And we have the process. We've got the processes to do this. The only issue that we're working on right now is scale and cost, really. But it is a really solid potential. And like I said, the steps for this one are fairly simple. It's find the protein, find the code, boom, make more of it. There's no sort of, it's not a case of it like having to grow and filter it in those certain ways. You can filter this, but it's, you do have to purify it. But from what I've read, it seems to be easier to make more and purify it in comparison to the other options. And literally the last section that I've got here was just about fast tracking a vaccine, which we've already spoken about. But I do want to end on that we've spoken about how to make a vaccine today. And although it's felt like it's felt like we've been talking about this for 10 to 15 years. We've actually not been. No, so it feels like we've been about it for a long time. But this process that we've just spoken about in the past, however long this episode is, can take 10 to 15 years. It can take a really long time. But shortening that isn't cutting out all the safety bits or all the sort of regulation. Like we said, it's just cutting out the bullshit and the waiting for money.
All the waiting times and
it's exactly
waiting for money, waiting for people.
Yeah. It's like if your travel time, right? If you're traveling from home to work and you need to get 2 different buses and there's a 30-minute wait in between the bus, you're just cutting out that wait time in between.
Or you just get a helicopter. If it's really an emergency, what I mean is that this is
I get
what we're in now. Is it's like, okay, we really need to get to where we're going. Can't bother waiting for the buses. Can't even drive because there might be traffic. Let's just get a helicopter.
Yeah, but it costs a lot of money to get a helicopter.
Yeah,
you get a lot of money, but just get a helicopter. But that's the thing.
I got a helicopter once for a documentary. It was incredibly expensive.
So yeah, that's the thing. Don't be worried about a vaccine being fast-tracked because it doesn't mean that they're not caring about the safety. They're just moving as quickly as they can through the bits that can be shortened. And a bigger budget and a bigger scale means that you can move things a lot faster. And there is a lot of money going into a specific vaccine right now.
Dolly Parton. Thank you, Dolly Parton, for your £1 million donation. Brilliant.
I was
work.
like, what about Dolly Parton? Yes, she does have a lot of money. I don't think that's affected her scale, but yes. No, Dolly Parton, well done. Good job.
She gave $1 million.
Good
work,
I didn't know
Dolly.
that.
Yeah,
oh, good on you, Dolly.
On the special thanks for who do we have to thank for this, the contributions for this vaccine? It says Dolly Parton Foundation.
Yeah,
it's lovely.
Ms. Parton.
Actually, if you're listening to this right now and you want to sign up to our Patreon, but you've been waiting for the moment to do it, now is the moment to do it and make the name Dolly Parton.
Hell yes.
If you do
we
that,
have to thank Dolly Parton in the next
was
episode.
Mark complete. Next will be Dolly Parton.
The first person to do that, we will send a personalized little thank you video to. In fact, not just the first person, actually anyone that does that and says they're Dolly Parton on Patreon, we will send a personalized thank you video to.
But it will be addressed to Dolly Parton.
Of course it will be addressed to Dolly Parton. It couldn't be addressed to anyone else. So that is how to make a vaccine. That was what it was called, and that's what it said in the tin. That's how you make a vaccine from start to finish. That is the end of the show for us today. We do just want to remind you that we have some calendars that you should definitely go and get.
Do we actually have calendars?
Yeah, we do.
When you're not lying.
Well, okay, I'm not lying at all. And I say we've got calendars, but we very well may not have calendars soon. Because they're all going.
Well,
they're
half
flying
of them have
off
already
the calendar
gone.
shelf.
Flying
exactly.
off the shelves, that's right.
They're simply flying off the calendar shelf. So you must buy one as soon as you possibly can. Otherwise, you'll be without a calendar. And then what day will it be? You won't know. You'll never know what day it is. Come 2021 or 27.
Did you know we invented the calendar? We're the only calendars that exist are the SCI GUYS ones.
That's very true.
How will you keep track of the days?
You simply cannot prove otherwise.
Time will cease to exist for you if you do not purchase a calendar.
And the thing about the calendars is, the really, really cool thing about the calendars is, as well, is that if you're a patron, you get a sexy little discount on those calendars, don't you?
You do.
It's just one of the little perks that you get for being a patron. You get a little discount on some merch. You get a little bit of bonus episodes. You get to vote on episodes. You get to do lots of stuff. So head over to patreon.com/SCI GUYS and check that out. Thank you for watching. You can find the full references for this episode in the description. Subscribe for new episodes every Sunday, and why not leave us a nice wee comment? You can support the pod at patreon.com/SCI GUYS, or you can find and contact us at SCI GUYS Pod on Twitter, Facebook, Instagram, and TikTok too. I'm not Corey everywhere.
I'm Champion everywhere.
I'm like Carforth everywhere.
Get vaccinated. Vaccinate your kids. Vaccinate your dogs. Vaccinate everyone.
Vaccinate grandma.
Except for the immunocompromised. That's bad for them.